Hey AP Chem, activation energy today. We're going to start off with a discussion about temperature and rate to remind you that rate constants change with temperature. Rate constants do not change with anything else, not concentration, not pressure, temperature only changes your value of K, and we're going to look at how today and how it's related to the energy it takes for a reaction to get going. If you had me for organic chem, we talked about activation energy at the end of biomolecules when we mentioned enzymes as biological catalysts. We're going back to that. If you've had that class, this diagram might look familiar, but first we're going to mention the collision model in terms of temperature. The collision model says that molecules have to collide to react. That makes sense. You can't decide if you like someone or hate someone if you've never met them. I know people who try, but in terms of molecules, what ends up happening is that collisions between two molecules sort of have a constant rate of reaction, that X number of collisions results in X number of reactions. It's tough in a lot of cases to change how many collisions are successful. Instead, if you increase the temperature, you increase your number of collisions. You don't increase your fraction of successful collisions. You just increase how many times you try. If I say, okay, you have 100 mini quizzes in a quarter to get 25 right for 100, that's great. You can get your 100 pretty easily, but if I say, okay, you've only got 25 chances, if the number of chances is lower, it's less likely that you'll get that many right. If you have to be perfect, it's way tougher than if you get 4 times as many chances that you need. And that's how molecular collisions work in terms of reaction. The more chances you've got, the more product you make. Easiest way to get more chances is to increase your temperature, increase your collisions a la kinetic molecular theory, and go for there. So that's where we're starting, and that idea is going to follow throughout today's lecture. Activation energy. If you're a cartoon fan, in the days that they were politically incorrect, when it was okay to squash a roadrunner, we were good with that. And he would just, Coyote would blow on his thumb and poof back up no matter what went on top of him and go about his way. Wile E. Coyote was loving pushing the boulder to the top of the hill and letting it roll down on the roadrunner, even though he always somehow missed and got himself or got an anvil dropped on him or whatever. If you've not watched those, YouTube Wile E. Coyote and the Roadrunner, there's days of binge watching. But what Wile E. Coyote was doing was putting energy into the boulder to get to the top of the hill in hopes that the energy then would be greater, carrying the boulder to the bottom, beep, beep, zoom. Never worked. But for us, this energy hill at the beginning of a reaction is our activation energy. The energy required, and you'll see it as E sub A, activation energy. It's the energy you have to put into a reaction to get it going. It's the kickstart for the reaction. It's real. Reactions usually aren't just like, ugh, with no energy added. Sometimes less energy is required, but usually you've got to get things going. When you look at a graph like this, you'll always see reactants at your left and products at your right. This reaction is exothermic. It's giving off heat because my reactions, or giving off energy, my reactants are at a higher energy level than my products. If this reaction were endothermic, reactants would be below, products above. We should realize by now that endothermic reactions are rough. Like, that's usually not ideal. Remember, increase in entropy. We like exothermic reactions. We like things that release heat, and normally we will. There's another important variable, another important piece of information you can get from here. And this is your change in energy. It says change in delta, it's delta H in the picture in your packet. But with this, that delta E is a change in energy specifically from reactants to products. Not counting the energy you have to put in to go up to activation energy, not counting your activation energy. Reactants to products, your change there is delta E. What goes on up here is a temporary thing. It's called the activated complex or the transition state. I usually call it a transition state. And It's rough. It's rough. It's like if you throw jello at a wall for that 1 second the jello dangles and just you can't. It isn't going to stay like that. The activated complex or transition state is a molecule that is really unfavored. It's usually some kind of mishmash of reactants, like you grabbed your reactants and went like this, and they stuck for just a couple nano pico little seconds. This is worse than millimolar, minimolar. It's worse than that. These last for a fraction of a second and are gone poof. They're not molecules you would recognize. They're ugly things, like ugly, just piled up. And unfavorable in terms of energy, in terms of bonding. They bad. They real bad. So they go away quickly. But you need the energy to get to this transition state in order to proceed to your products. So they are a necessary evil. Do you find them in mixtures? No. They get ripped apart. There is no way. It is like when my desk at school is clean. Right now I am standing on an anatomy book, a sweatshirt, and some AP Chem answers, and a Santa Claus that you can't see. I can clean this room. It will last about 3 seconds. That's my transition state, my perfect cleanliness. So for molecules, it's just as unlikely that it stays. So let's see what we've got here. Flipping page. Your rate of a reaction is going to be determined by the magnitude or size of your activation energy. Reactions with larger activation energies are going to be harder to get going, and they'll be slower. If you have an activation energy that's like this, you got to go up that hill before the boulder's going to roll. But if you just get a little bump, it's going to be a lot easier and your reaction will proceed more quickly. The calculations here with your fraction of molecules are nice. You'll do one. In real life chemistry, they're okay. They're not the focus of this section of the course by any means, but I wanted to show you. I'm not putting them up because they are one of those things. They're a plug and chug thing. The fractions of the molecules that for the equations for the fraction of molecules that have an energy equal to or greater than activation energy. So the fraction of molecules that will react successfully by this, F is like fraction, E, that's as in undo it with natural log, that's E, calculator E. Your superscript on E, activation energy divided by RT. The R is the weird one. It's not the one, the 0.0. It's 8.314 joules per mole Kelvin because you want to talk about activation energy. So you need the R with joules in it because we're using energy. Your fraction equals E to the negative EA over RT. Sub in your numbers and go. Not a thing. Remember, this is your fraction of molecules that can react, that have the enough activation energy. Keep going. The Arrhenius equation. I learned this and I was like, oh, cool. Okay, so your fraction of molecules that will react is not something, again, you'll be calculating every day. I learned to do it, and I'm going to show you how. What makes up the reaction rate data, the factors that determine it, are more important. Fraction of molecules with enough energy. That's what we calculated above with the negative EA over RT, the E to that. Number of collisions per second, remember, is affected by temperature only. And, well, I shouldn't say only because it's affected by temperature. It's one of your big factors that's affected by temperature. And the fraction of collisions that have the correct orientation. If I'm trying to flip a bottle, the cap land, my number of correct orientation collisions would be when the cap hits the table. If I'm hitting the bottle on the side, I'm not going to make that flip. It's not going to, correct orientation. So the Arrhenius equation, what it's going to do, if you look in your notes, it's calculating the rate constant from these things. This is where your rate constant comes from. Normally, you're given your rate constant and you don't use this. K usually just appears, but this is how you can calculate it. A is your frequency factor, related to the frequency of collisions and the probability that they're successful. So that's going to be collisions per second and correct orientation. Numbers 2 and 3 are the majority of your frequency factor. You then just pop in your fraction. The E to the negative EA RT, EA over RT is from above. That's my fraction of molecules with enough activation energy. So what the Arrhenius equation looks at is frequency factor, my number of good collisions, times the number of molecules that would have enough energy. So as the activation energy increases, reaction rates decrease. You can do this activation energy thing with a graph. You can figure it out with a graph. I'm going to go through those notes quickly. I will post my work on the graph. I want you to try to work through the whole graph thing. I'm going to talk about it and what I would do. But there's a how-to posted also on the what I did. It's something about activation energy graph, I think is the title. If you graph ln of k equals negative EA over RT plus ln of A, you get this. You'll get your activation energy from here. You'll get your slope. It's all related. So when you do this graph, here's what's going to matter. What I do is I put ln of k on my y-axis and 1 over t on my x-axis. ln of k, 1 over t. That's what's going to matter because the rate constant depends on temperature. The rate constant increases as temperature decreases. So that's going to take care of that. And by taking the ln of k, we're going to get a straight line for our graph. And that's what's important. Your slope's going to be negative EA over R, and you know R, 8.314 joules per mole Kelvin. So you'll be able to get your activation energy from that. Very nice. The equation is there, and you'll be able to follow along. At the bottom of the page with the graph in your notes, the first one is a useful equation, ln of K1 over K2. So if I'm comparing rates at two different temperatures, ln of K1 over K2 equals EA over R, and then my parentheses 1 over T2, the second temperature, minus 1 over T1, the first temperature. The rates in the problem go K1 over K2. My temperatures are 1 over T2 minus 1 over T1. You will need to learn to do those problems. They're way more straightforward than graph, graph, graph. On the next page, we've got a graph for you to try. First order reaction, so it's going to be great. We're going to need, though, ln of k and 1 over t, and I gave you data in k and t. So you'll need to switch those over, take the ln of k, take 1 over t, and graph. Get your slope. That's going to be your negative EA over R. So calculate your slope. Since it's a straight line, you can do any points. The mini quiz, we were looking for instantaneous rate on a curve, so we needed a smaller range. This one, you can just go with it. Once you graph it, go with it. Any section will have the same slope because it's a straight line. Get your slope, divide by R. Remember, joules and kilojoules, you're going to be in joules with the R you have. Give that your best shot. Check your answer with me. Try your practice problems, and I'll post your answers. And that's what I got. Activation energy.